We are trying to find the magnetic field above a ring of current. So let's draw our ring. And we have our central axis here, the central point of our ring, and we are going to be interested in the magnetic field somewhere up here. Now, for this particular ring, we can sketch out some of the geometry. So we are going to give the ring a radius of A, which we will label here. And for all of these problems, similar to what we saw with computing electric fields, you don't want to pick a special point. And for the ring, we can just kind of pick any little point along the ring. That's going to be our little tiny piece of the current. So let's call this DL. And we'll just assume that it's going in a counterclockwise fashion for our current here. And now we want to make sure that we label things really, really well, because that's going to make this calculation a lot easier. So this is our distance away from our point of interest up here, P. So let's call this P. And that is some height Z above the central axis. And so that we'll call R. And if we wanted to make this a vector, it's R, where the magnitude of R is going to be A squared plus Z squared, just from Pythagorean theorem. We can use this angle, theta, which we know now because we know A and we know Z. A is just the bottom part of this triangle here. So we can calculate this angle theta, and why that's going to be important is that when we come up to our point of interest, well, our little tiny unit vector, which is r hat, points in the same direction as r. And if you remember the Biot-Savart law, the thing that we're interested in is dl crossed into r. Right? Well, what is that vector going to look like? Or excuse me, dl crossed into r hat. What is that vector going to look like? Well, if dl is sort of pointing in this direction, or you can almost think of it as kind of into the page there, dl crossed into r is going to give us a vector that's perpendicular to both r hat and dl, and is going to point sort of in this direction, right? So this is something that, again, needs to be perpendicular to DL, and that's going to be tougher to visualize because we're in just 2 dimensions here, and is also perpendicular to R hat. Now, if it's perpendicular to R hat, I know that this vector, this angle, has to be a right angle. Let's extend our z-axis a little bit here. All right, now we can do a little bit of geometry because this angle is also a right angle. And so this angle here is 90 degrees, 90 minus theta. And if that's 90 minus theta and this is 90, then this angle here has to be theta. And why we care about that is that it's going to set up the next part of our... That's a bad theta. It's going to set up the next part of our calculation, which is looking for symmetry. And so if this is the direction of our magnetic field at point P for this particular piece of the ring, as we swoop around this ring, we're going to notice that really the only angle or the only component that survives is the z component, right? So the z component survives integration. And that means that we can recast our little piece of the magnetic field as really just the z component that we care about. And that is going to be dB our little piece of the magnetic field, times the cosine of theta, because we want that piece that's adjacent to the z-axis. And what's great about the cosine of theta is also a over r, which we know from the triangle that's part of the ring there, and that's going to be a over the square root a squared plus z squared, which in this case, all of these things are constants. The other thing that we know is by the looking at the cross product here, dl crossed into r hat, well, that is going to be the magnitude of dl times the magnitude of r hat, which is just 1, times the sine of theta, which is the angle between those two. And that is going to just yield a dl in the k hat direction. All right, so this term is 1. This dl, the sine term, is one that doesn't necessarily need to be 1, but what we do know is that when we add everything together, we're only going to be left with a z component. All right, so now let's get to the integration part. And I should say that when you do these problems, the best thing that you can do to help yourself is to draw a clear picture. And please check out the picture that I drew in the notes as well. All right, so we're going to add this together and set up our integral. So the magnitude of the magnetic field, we already know it's going to point in the k hat direction, so we can just deal with magnitudes here. That's going to be the integral of the z component of the magnetic field, which is going to look like dB times the cosine of theta as we go around the ring. And this, we're going to use the Biot-Savart law, so mu naught times our current over 4 pi as we go around that ring is going to be dl, so the piece that's left over from our cross product, over r squared, which is part of the Biot-Savart law, times our cosine term, which we said was a over r. And now we want to factor out anything that's a constant. And in this case, there are a lot of constants. So a is the radius, that's not going to change. And we could take a 4 pi r cubed outside. R is not the radius here, it's our distance to our point of interest. And we are just going to integrate dl over the loop, over our ring. All right, so this gives me a mu naught I times a over 4 pi r cubed times, now what is this integral? Well, this is just the path that we're taking around the loop, and so in this case it's going to be the circumference, and so that's going to be 2 pi times a being the radius of our loop. And we can cross a few terms out here, the 4 pi and the 2 pi, we're going to be left with a 2 down underneath. And that is basically as far as we can go with this particular problem. So we have a mu naught I times a squared, those a's combine, over 2 times a squared plus z squared. And that is raised to the 3/2. That's our r cubed term. And this is in the k hat direction due to symmetry. So that is our magnetic field at some height z above the central point of the ring. And we can also check. Let's check and make sure at z equals 0. What do we get? Well, at z equals 0, we have all these terms stay the same, a 2, And now we have a squared to the 3/2. The z disappears. And so that's going to leave us an a cubed. And that reduces to mu naught I over 2a, which is the magnitude of the magnetic field that you get when you're dealing with just the central point of the ring. So that checks out.